Here's another example of us finding a volume of a solid of revolution by using this slicing into disk shapes method. So here, this one's from your textbook, we've been given a curve. It happens to be x plus x cosine x. And we're asked to revolve it around the x-axis and find the volume of the solid that is produced. So I'm going to use my steps. I'm going to shade in this region. They already shaded it for me, so maybe I won't shade it in. I'm going to draw in my axis of revolution in red. Been told we're revolving around the x-axis. There's no reason to make your red go further in the picture. It doesn't hurt. Alright, I'm going to imagine taking that shape and flipping it over that axis I drew. So this is like you practicing reflections, which you probably did in geometry. Okay, doesn't have to be perfect, but that's the shape I would get if I revolved it 180 degrees and then left it flat. So what's it going to look like if I take a cross section? So I just want to point out, because it's going to be a little different in the next set of videos, the shape, which your book shaded in brown, I borrowed your book's picture. Notice how the shading goes all the way up to and touches that axis of revolution. That's going to be key here. It makes our work a little easier than what's coming up next. So notice I'm going to take my slice and I'm going to make my slices green. Doesn't matter what color you pick. I'm going to start with green and stick with green. I'm going to start my pen at my axis of revolution. I'm going to draw toward the function whose equation I know. I'm going to come back down around behind the axis of revolution to hit the reflection, and then come back up to where I started. So that green slice, it's not a circle, but its face is a circle, and it has thickness. So we call that a disk. What I want to do is try to write an expression for the radius of that disk. Notice I was told that my revolution was about the x-axis. I'm always going to take my slices perpendicular to the x-axis. Alright, so I'm going to imagine drawing in the radius of that green disk. Well, the radius goes from the center of the circle, which would be on the axis of revolution, goes out toward the edge of the circle. So for me, that's going to be where my slice touches, that wasn't a super picture, where my slice touches the curve whose function I have a name for. So that blue radius is going to be the radius of my slice. Can I write an expression for the height of that blue line segment no matter where along the x-axis it gets drawn? Well, no matter where I draw that blue radius, its top is going to touch f of x, and its bottom is going to touch y equals 0. So in every case, the height of that blue radius is going to be f of x. I can write f of x minus 0 because I need to find that distance, but I'm just subtracting 0. I don't actually have to write it. So I'm going to write f of x as my radius. Now I can write my integral. The volume of that slice is going to be, since it was shaped like a cylinder, a very short cylinder, pi r squared times the thickness of the slice is going to be a very small change in x. You could write delta x here. When we put it in an integral, where that's us imagining we're going to take infinitely many slices, and that's going to become delta x. So my volume is going to be the sum of infinitely many, infinitely thin cylinders whose thickness is dx, and each has the volume pi times r squared times the thickness. Now, I'm showing lots and lots of steps just so you see where these expressions come from. If you're ready to write the integral, go for it. You're going to write volume is the integral from, my integral is in terms of x, so I need x limits. It's going to be from down there is -2 to +2. There, this time they told me the limits. Pi, instead of r, I'm going to use f of x squared dx. On the free response section of your AP test, this probably gets 2 points. One for making an integral with the correct limits, and one for getting a correct integrand. Now, obviously, this is not something I can type into my calculator. Your calculator won't know what f of x is, but the next step would come from actually evaluating this integral. This integral, notice it's going to have this quantity x cosine x added to x. That's all going to get squared. It's not an integral we're going to be able to find by hand. So they would not expect you to integrate this one by hand. You might get to use a calculator, or they might just say write, but do not evaluate an integral. So it's your integral for the volume of that solid, which looks like a flower vase. All right, so if you really wanted a formula for what's going on here, you might write this formula. If you can slice your solid perpendicular to the axis of, perpendicular to the axis of revolution, and every slice is going to look like a cylinder with thickness, we call it a disk, then the volume of each cylinder is going to be pi times the radius squared times the thickness of the slice. And in this case, where the x-axis was our axis of revolution, the height is going to be the y value, which is going to be the whatever function you happen to have. Notice I wouldn't actually be able to integrate here because I have both x's and y's in my integral. A and b have to be x values because we're integrating with respect to x. It will be your job to find a formula for the radius that's written in terms of x. Even though you need the height, like a y value, you need to write it in terms of x so that we have one variable in our integrand and we can integrate. I don't love focusing on this formula because, remember, that's what happened to me in high school. I didn't understand the formula. I just tried to plug random stuff in. It just didn't work. But if you like it, feel free to, if it helps you, use it to help you. If instead of taking our slices perpendicular to the x-axis, we needed to take our slices perpendicular to the y-axis, what would change? We'd still have disc-shaped slices, which have the same volume, pi r squared h. It's kind of like what you did with your bucket. But instead of writing our integral in terms of x, we would write it in terms of y. And the radius would be horizontal, which implies that it comes from x coordinates. So you could think of this if you need a formula. I'd rather practice it and make sure that we understand where all those numbers come from. So check out this problem. Here's a curve, x equals 1 over the square root of y. This is kind of nice because sometimes they'll disguise it a little more and just give you a regular function in terms of like y equals a function of x. Here they've already written as a function of x for us. That's kind. Now we're going to revolve this curve, this curve, around the y-axis. They've given us these limits. Okay. So here's what I like to do. We're going to revolve it around the y-axis. We're going to see if we can write the integral that goes with it. So I'm going to shade in my region. I picked gray just because it might look like your pencil shading. I'm going to draw in the axis of revolution in red. This time I'm revolving around the y-axis. We try one more time. This is harder than you would think. Alright, and now I'm going to reflect that shaded region over the x-axis. Okay, I like to call this problem the lampshade. Okay, so I happen to already have a slide that had the little green disc, well, at least the radius of the disc drawn in. So I'm going to move my sketch in a second, but do you see how I've swept out a solid that kind of looks like a lampshade? And if I'm going to take my slices perpendicular to the axis of revolution, that means I'm going to slice horizontally, which means the thickness of the slice is going to be a very small change in y. I'm going to write my integral with respect to y. So I like to draw in the whole disc. And you can see that picture sketched in your notes handout. The radius, I usually do in blue, but this one happens to be green. I could draw that radius here. You can the way this is drawn, it's easy to see that the height of the cylinder is going to be a very small change in y dy. So now I'm going to write an integral to say that I'm going to add up infinitely many, infinitely thin disks whose height is so small it's essentially 0, and whose area of the face is the area of a circle, so we have pi r squared. Notice r comes from this distance. That x-coordinate is 0. This x-coordinate comes from this function. So here's my integral. V is the integral from 1 to 4. From 1 to 4 because I need y values for my limits. And I've been told the y values in this picture go from 1 to 4. So I could integrate this function from 1 to 4. Pi times 1 over square root of y, all raised to the second power. And this is with respect to y. Alright, if you were then asked to evaluate this integral, it's going to be your job to simplify as much as you can. This one's not too bad to do by hand, because 1 over the square root of y, when you square it, just becomes 1 over y. So this is a simplified integral. So notice the antiderivative of 1 over y is the natural log of the absolute value of y. But notice I'm going to evaluate that from 1 to 4. 1 and 4 are both positive, so that's why it was okay to leave out the absolute value bars. So it's going to be pi times natural log of 4 minus natural log of 1. The natural log of 1 is 0. Feel free to leave your answer like this. You can just write pi times the natural log of 4. If you're really excited to show off that you know your logarithm properties, you could think of 4 as 2 squared and bring the 2 down. I don't need you to worry about that at all. Final answer, pi times the natural log of 4.